we good? Welcome, everybody. Nice to see everybody here. So, I guess there's some interest in streams. Is that so? Cool. So, I'm here today to present some work that I've been doing lately and some things that I've been talking or thinking about. So, let's go through the obligatory agenda. So, first, there's going to be streams, and then streams, and then we'll wrap it up at the end with some streams, just so you know exactly what to expect here. So, let me first start this presentation with a question. So, what if we could, using Java streams, do something similar to this? So let's say that we receive some packets, and we want to make sure that the ones that we receive, that they are well-formed. They haven't been corrupted. And then, of course, we want to make sure that we receive them in the right order. So we want to reorder that stream. And we want to make sure that if we receive duplicates, then we deduplicate those. We remove the duplicates. And then we might have multiple distinct sequences of packages that we want to do something with. So we want to group them using some indication of whether a packet is the first of a sequence. And then we want to convert that into a request object. And then we want to, using some ideal highest number of concurrency, we want to call some backend service using that request. And we want to get the responses back as a list of responses. That, to me, is a very natural thing that somebody might want to do. So what if we could do that? First, we need to establish some common terminology here. So when I talk about Java streams, I talk about this specifically, whatever is under java.util.stream, and typically looks something like this, right? So we have some source of information, could be, in this case, it's a couple of strings, and then we have some intermediate operations. We want to do something with the source of elements in order to get that somewhere else. So in this, filter and map, they're intermediate operations. And then at the end, we have a single terminal operation. And at the end, we get a list of foo and bar here because we were filtering out that empty string. So just to make sure we're clear with source, intermediate, terminal, that's fine because that's going to be super important. The entirety of this, I will call that, in quotes, pipeline. And I call that in quote pipeline because that is not something that you can actually get a hold of. When you call the terminal operation, you get the result of the terminal operation. You don't get the pipeline. So it's a virtual construct. So I was talking about a lot of interesting operations that one might want to do with streams. But there's a lot of potential operations that you might want to do in certain circumstances, and in other circumstances, they might not be as useful or applicable. So there needs to be some form of balance. How do we decide how an intermediate operation ends up in the stream interface? Because the risk is that if everything goes in, then it's going to be really hard to find what you're looking for. So need to maintain some balance of what's available as built-in operations in the streams interface. So just as a question, has anyone here ever had a use case where you needed an intermediate operation on a stream that was not available? Any opportunity. So that's a fair amount of people. So I think it would be interesting to see how we could achieve that balance, because there's so many useful things that one might want to do with streams that is currently a bit difficult to achieve. So right now, we don't have reorder. We don't have deduplicate consecutive, we don't have group using, and we don't have map concurrent. So these are intermediate operations that do not exist right now. So the question becomes, should those be added? Should something more than that be added? Should something else be added? How do you decide? And who decides? And when do you decide? So let me pose another question. What if you could add any intermediate operation? That will be a much more interesting proposition here, because then we don't have to know upfront what anybody might ever want to do and add every single method to Stream. So what would that look like? Well, clearly, if we don't want to add any or every operation to Stream, we would have to have an indirection, so that any operation that anybody had defined themselves could be used with Stream. So there needs to be an integration point on Stream in order to facilitate that. So that would look something like this, right? So we're able to define reorder or any of the other ones and use some form of built-in method so that the Stream can use those custom implementations. What's interesting as well is one way that I tend to think about Java streams is it's sort of like a builder pattern. So until you get to the terminal operation, you're just building a stream pipeline. You're not executing the stream pipeline. You're building what you want it to do once it gets to the terminal operation. So you don't necessarily want to have a situation where you have to force evaluation earlier than you wanted just to be able to do what you wanted to do. So how can we make sure that we can build these pipelines as we need as Java developers? So some of you might be familiar with the collector API. So collect and collector is one of the terminal operations on streams. And one interesting question here would be, couldn't you just use collect and collector and that's done? You can just implement your own collector and all is good. You can have your own custom stuff. That's a great question. So to answer that, we need to look at this from what we need to achieve if we want to have the API of extensible intermediate operations. So what do we need? One thing is inputs and outputs to each operation, right? So you need to support both one-to-one. A good use case there is map, for instance. It takes one element in, produces one element out every single time. You want to be able to support one-to-n. So that could be an example of flat map or map multi. So you could emit 0 or a lot of elements as a response to a single element. You also want to be able to take multiple elements and only construct one single element out of that. And all of these variations where you might want to get, in some cases you get 2 and then emit 1, in one cases you get 3 and emit 5, anything under the sun. So it's sort of any to any. Think about it like that. So that's only one aspect. The other aspect is a stream doesn't necessarily represent a finite instance, right? It could be an unbounded number of elements. So we need to be able to support manipulating potentially unbounded streams. What I mean with incremental operation here is an important distinction. So imagine that you had a stream pipeline where each stage had to consume everything before it could emit its own output. That means that if you have an infinite stream above, how do you consume an infinite stream before you can output anything? So clearly that will never terminate. So by incremental, I mean be able to consume elements and produce elements and push those elements downstream. So incrementally working through the data set. And finite streams also benefit from incremental operation because you don't need to store those intermediate results anywhere. You just push them down the pipeline. Stateful or stateless. So a good example here, map, for instance. It doesn't need to remember anything between each element. So that's a good stateless intermediate operation. But you could have something else like limit that allows you to only consume a fixed number of elements. So that needs to remember how many elements it's seen thus far. So it needs to have some state that goes across each element that it receives. And then, of course, these might be weird names for this, but think of it like this. Some operations, such as limit, only wants to consume as much as it needs. It doesn't want to consume a single element beyond that. And that's important. And some operations can only consume everything. It cannot short circuit or exit early. And both of these also benefit from incremental operation. Yes?
This last thing is related because we are in reality speaking about the laziness of intermediate operation of streams, right?
That's a good question. So are we talking about the laziness of streams here? So it's not necessarily about the laziness of evaluation in a starting the evaluation, but it's about to be, so let's say you have a pipeline of 3 intermediate operations, and 2 of them in the beginning, they're greedy. They're going to consume every single thing that they see. But in the 3rd step, you have this frugal operation that only wants to consume, let's say it's a limit of 1. I only want 1 element. So if you consume everything before you emit anything in the previous stages, then you will never be able to transitively propagate that frugality across the pipeline. So that's sort of how I'm thinking about this. And of course, as we know, Java streams, they can both run in sequential mode or in parallel mode. So it would be really nice if there was a nice way to be able to make sure that operations either are parallelizable or that they are correct under parallelization, because some operations do not parallelize well at all. So in some cases, correctness is king, and it doesn't matter if you can speed failure up. And of course, at the end, there are some operations that only know what to do once they know that there's going to be no more elements coming through. So think of something like sorted, for instance. How do you know that you're done sorting something if another element could show up? So being able to react to end of stream for the operation itself is an important characteristic in order to be able to represent as many intermediate operations as possible. So, everything clear here? Some weird names, but should be everybody okay? Good? All right, so let's look at collector then. We have collector, and collector is an extensible API for terminal operations. So how does that match up to what we're expecting to have to need, or what we're expecting to need in order to have intermediate operations? Well, first we need to look at what is the collector? How does it even work? So a collector is an interface. It takes a parameter type T, which is its input type. It has a type parameter A, which is its state, so the thing that represents what it collects. And the R is the return type or the result type of the collector. And you can think of this as, for all intents and purposes, it's 4 methods that return functions. So first, you have a method that returns a supplier of A, so you can construct this state that you need to remember. You have a by consumer, so that's a function that takes the state and the next element and accumulates that state into, or accumulates the element into the state for each element. And then there is a combiner that under parallelization are able to combine parallel results into a single result, or parallel aggregation into a single aggregation. And then at the end, we have a finisher. You call that with the state at the end of the computation, and that gives you the result. All right. So if we look at what we can do with these 4 functions. Unfortunately, we can't represent one-to-one because collector doesn't emit anything. So it only accumulates. And we cannot really represent 1 to n because it doesn't emit anything. We could collect it into a list of sort, but that is only available at the very end. But what collector is really good at is representing many elements to a single output. So getting that result, the to list. Get all the elements into a single list. And it's, of course, since it's not good at the 1-to-1 or 1 to n, it's not really good at the n to m either. All right, so with collector, we can only consume finite streams because collector collects everything that it gets. So it's a greedy operation. So it means that if you're collecting on top of an infinite stream, it's going to take a while. And then what's good is that if you are stateful, you are also stateless because you could have your state be void. So since collector is stateful, it also supports being stateless. And as I said, it consumes everything it sees, so it's clearly a greedy operation. And it's not incremental either because it gets everything at the end as it is a terminal operation. What's good about collector is that since it has this combiner, it's parallelizable. But what's not necessarily that good is that if you want to represent something that doesn't parallelize well, but you still want it to be able to work if the stream itself is parallel. It might not get parallelized, but you don't want it to blow up. You need to provide that combiner anyway. And then, as you saw, we had the finisher, so we're able to get a callback of sorts at the end of the consumption so that we know that we're done. So that's good, but clearly we're not ticking all the boxes here. So let me introduce something new. So imagine that we have something called a gatherer, which is strongly inspired by collector, and we have an accompanying method called gather on stream. So remember back when we saw the 3 question marks for our method, that if you plug in gather instead of the 3 question marks, that's how that will work. And this would be an extensible API for intermediate operations. So it's clearly related to collector in some way, so let's figure out what that is all about. This looks familiar, right? So we looked at the collector. It had 3 type parameters, T, A, R, same here. The main difference here is that the R is not the end result, which is a single result, but it's the type of output. So we have, instead of the supplier, this is called the initializer, different name just to reflect what it does, which is slightly different from what collector does. So somehow we need some way of being able to obtain where we accumulate our state into if we are stateful. We have, instead of having the by consumer, where we get the state element, or the state object and the next element, we have something called an integrator. And you can think of an integrator as a function that takes 3 parameters, the current state, the next element, and a reference to the downstream, the next stage. And it returns Boolean. And the reason why it returns Boolean is to be able to say that I do not want any more elements. So if it returns true, it means that it wants more elements. If it returns false, it says that I do not want more elements. So that allows us to, as you process an element, to be able to respond to say, okay, I'm done. We still have the combiner. That's useful in order to be able to parallelize this. And if we can combine our state elements, then we should be able to parallelize as well. And we modify the finisher a bit. So instead of being a function from A to R, it's a by consumer of A and a downstream of R, so that we get the final result and we have some means of being able to send something downstream in response to knowing that we will never get any more elements. So it's fairly close to collector. So the differences here is our integrate method and finisher, they have the downstream handle, and downstream has 2 methods on it. So one way of pushing an element to the next stage, to the downstream, and that also returns whether the downstream wants more elements or not. So that allows you to transitively propagate that signal of, hey, something far down there does not want any more elements, so let's make sure that we don't want any more elements either. And then there's a method that allows you to interrogate the downstream whether it's in a rejecting state, because at the end of processing, for instance, it might not be necessary to do a lot of work if you know that nobody's going to be able to accept it anyway. And then, of course, new name here, like integrator instead of by consumer. I don't know which name is better, but the integrator is what is processing each element. So it's a very core component here. And it has a single method called integrate, takes the state, the next element, and the downstream. Is this clear so far? Lots of new thingies. Just want to make sure that everybody's on board. Cool. All right, final difference. As we said, difference between the finisher. We don't return a single result. We have a handle so that when the upstream doesn't have any more elements for us, we can produce more elements to our downstream. So it's the main difference. All right, so how does this look in practice? So as a thought experiment, imagine that Stream did not have the map method. As a very simple intermediate operation, let's see how that will be representable as a gatherer. And I love JShell, so I have to see that. All right. So first, since every single use of map typically has its own function, we need to create some method that takes that function and gives us a gatherer. So here we get a mapper function into our map method. Our map method returns a gatherer from T to R, and the reason for the question mark is that the consumer doesn't care what the state type is. It's the same with collector. So we need to define an integrator. And what does map do? It's stateless. So we have void as our state type. And we have T's as input elements and R's as output elements. So that's what we give as type parameters to our integrator. We say that the first element here, which is of void type, it's unused, we don't need that. We get an element, and we get a handle to the downstream. So implementing map using gatherers is we push to the downstream the result of applying the element using the mapper. And then we take that integrator and we pass it into the factory method of, same as collector if you've used that before, collector of. And that's how we implement map. And this is also parallelizable because this has a void type, so we know that it's stateless, and we haven't given any restrictions on a combiner. So this is parallelizable. So how would we use that then? So instead of the 3 question marks, we use gather instead, and then we call map with the lambda that we want to use. In this case, we have a stream of 1, 2, 3, 4. We want to add 1 to each element, and we want to create a list of the result, and that would be it. So that's the simplest gatherer that I could think of. It gets more exciting, I promise. All right. So let's take something slightly more sophisticated. So map multi is you can think of it as the imperative equivalent of flat map. So how would we implement that? It's 1 element to n elements. It's stateless. It doesn't need to remember anything between each element. And it's also parallelizable. So we define map multi here. We return a gatherer, same as before. The difference in the signature here is that map multi takes a by consumer of the element and a consumer that represents the downstream. So how would we implement that? Well, we need an integrator, of course. We need to do something with each element. Same as before, we're stateless. We're going from T to R, so we have the same signature as before. And the difference here is that since we have a by consumer rather than a function, we're applying the element, so the next element, and our consumer is actually pushing to the downstream. So when the user code calls the consumer that it gets when applying the mapper, that is doing the equivalent of downstream push of that element. It will make sense soon, I promise. And then, of course, in this case, we are never going to stop early. We're greedy here, so we're going to say that we always want to have more elements. Create a new gatherer of our integrator, and then how do we use this? All right, so let's say that we have a stream of 2 lists. So first 1 and 2, and then 3 and 4. And what we want to do is to create a stream that is 1, 2, 3, 4. So we have a stream of lists. So for every element that we get, we do the consumer for each that list. So it's essentially passing the consumer part into for each of each list. And that gives us 1, 2, 3, 4. So that's map multi as a gatherer. All right. Let's take something more interesting here. Let's say that we didn't have limit. So what is limit and how would we implement that? Just to make sure that we could, if we wanted to. We define a method, take a max size that we want to have, use a long in this case, and we're now a gatherer from T to T. So we take input elements in and we pass them out for as long as we haven't reached our limit. But now we need to have state. We need to remember how many elements we've seen. So let's define a class called count, and let's keep track of how many elements we have left until we're done. We can define on our state class as well an integrate method. So what happens when we add an element to our current count? So we get an element in, we have a downstream in, and what we do, of course, this is rather straightforward. We look and see, are we able to pass anything more downstream? If we are, we decrement how many we have left, and then we push that element downstream. And of course, if the downstream doesn't want any more elements anymore, we can return that as well. So that's fine. And if we're done, then we say that we don't want any more elements. And then we can actually create a gatherer using a new count as our supplier and the integrate method on that state as the integrator. So this is just a pattern that you could do. And that's it. So that's how you could implement limit as a gatherer. All right. There are multiple ways of doing it. You don't necessarily would have to use this sort of method, the of factory method. You could also implement the gatherer interface directly. That makes sense in a lot of cases as well. So I've just highlighted here the code that is familiar from the previous slide, so you could see where it would go. So gatherer is an interface. It has 4 primary methods that return functions. So in this case, we want to make sure that the initializer is creating a new count instance each time we instantiate it, and then our integrator is a lambda here where we get the count, the next element in the downstream, do the checks on the state, and do the same thing as we did before. And you could also see how you could start with having something as lambdas and anonymous things and move them into named things inside of the method first, and then move them as first-hand constructs available as a public API, for instance. So there's a maturement period or stages that you could go through if you decided that you wanted to expose the classes themselves. All right. So how do we run this? We have four functions. How do we run this? So let's go through first the textual representation of what it means to run a gatherer. So first for the sequential case. First we need to decide what are we going to do with the output. So we get a gatherer, where are we going to pass its output? So we need to create some sort of handle that represents the output. And then we need to initialize the state. So we need to call the initializer, and we get the supplier, and then we do get on that, so we get a new piece of state. Then we need the integrator, so that we know what to do with each element. So we call integrator on the gatherer. And then the main loop, where while there are more input elements, and while true is returned from invoking integrate with the current state, the next element, and that downstream handle, we repeat. For as long as we want more input, we give it more input, if we have more input. And then at the end, when we either didn't have any more input or didn't want any more input, we call the finisher with that state that we had and the downstream handle. So, this is text. I don't like text necessarily, so let's look at code. So we define this evaluate method. It takes an iterator of t's, so that's our input source. We have a gatherer from t to r using some state type that we don't necessarily need to care what it is. We just need to make sure that we can give it that specific type. And then we have a consumer representing where we want the end results to go. So, as we said previously, the first step is to create a downstream handle. In this case, our downstream handle will relay whatever we get to the output consumer that was passed in, and it always wants more elements. So that's fine. We get the state, we get the integrator, and for as long as the source has more elements, the integrate method returns true using the next element and the downstream. We just repeat. Then at the end, we apply the state and the downstream to the finisher, and then we're done. So invoking this, let's say that we have a list of foo, bar, and bass. We get the iterator out of that. We create this sort of anonymous gatherer here. The only thing that it does is take strings and converts them to uppercase. And we want to send that to system out. And that is what it does. Now, parallel evaluation of these things is not strictly as easy as the sequential version. So I will go through the sort of loosely spec'd thing here just to give you a sense of how it works, and then I will illustrate better how it actually works. So we have some input stream of elements, or an input container. And if we can split that into parts, and split them recursively into parts, then we continue to do so for as long as the chunks are larger than what we want. So make sure that we get them sliced and diced up into small pieces. And for each of these pieces, let's sort of pretend that that's a sequential evaluation, with the main difference that we don't call the finisher for each leaf. So we create, as usual, create the downstream handle, get the state, get the integrator. While we have more things in our little piece, we apply those, and then at the end, we recursively merge back up using the combiner. And then at the very end, when we only have one single thing, we can call the finisher on that, and then we're done. So just to illustrate how that would work. So let's imagine that we have, and this is a stream from 0 to 9, and we want to evaluate that in parallel. So what we do is we split it into equal parts here, and then we split it again into even smaller parts, and then clearly it's not going to be easy to split 5 into 2 equal halves, so they aren't of equal length. And then we decide that now they're small enough for us to parallelize this. So let's say that we have an operation that just sums things up. So it's a parallel sum operation. So each of these leaves here, the state will be 3, 7, 18, and 17. And when that is done, we recursively combine them at each of the upper branches. So we combine the 3 and the 7, and the 18 and the 17, and then the 10 and the 35, and then we have 45. We pass that into the finisher with the downstream, and then we're done. All right. Simple enough, you would think. So how do you do this if the operation can say that it doesn't want any more elements? So let's say that we wanted to parallelize take while. That will take a stream and output the elements that go in for as long as it hasn't seen 4 in this case. So you would expect this stream to be 0, 1, 2, 3. And that's done. And how do you parallelize that? So let's split it again. And then when we see that it short circuits and says that it doesn't want any more elements, we remember that. So the first leaf, it saw all the elements and it didn't say anything. For the second leaf, it saw 3 and then 4, but hey, it didn't want 4, so it stores 3 and remembers that now I'm done. And then the others, they saw something that was 4 or greater immediately, so they don't have any output, and they also record that, hey, I didn't want any more elements. So now we have this rather imbalanced tree here, right? So we recursively merge that upstream as well by concatenating the output. And it's interesting because if you do this recursively, then you can say that only merge whenever the right-hand side hasn't, or the left-hand side hasn't short-circuited. So you keep propagating whatever you want to keep up the tree. And you still do that on the right-hand side because it's good to remember that you did short-circuit. So at the end, you arrive here, and then you're done. So that's the exact same result that you would get if you would do a parallel or a sequential evaluation of this. So, but Viktor, I hear you say, how much work didn't we do here that was completely unnecessary, right? We did a lot of stuff here. We parallelized. Let's see if we can find that thing here. So all of the work we did on the right-hand side of the tree was unnecessary work, right? So even if we parallelized, a lot of the work that we did, or almost the majority of the work that we did was waste. So clearly, we do not want to do unnecessary work. So what we actually end up doing is whenever something sees a short circuit, it tries to cancel everything that is to its right-hand side. So if work hasn't started yet, that could be completely canceled and that wouldn't be wasted. But it's still, whenever you have short-circuiting, parallelization is always a bet that it's worth it. Because you could imagine, if you, let's say that it would be less than 1, you would only ever need to read the first element of that stream and then you would be done. So there wouldn't be much to parallelize in the first case. All right. So now we know what a gatherer could be or is, but how do we deal with the situation with which methods do we add and where and how? Well, I think it makes sense to have some built-in gatherers. So that there are some pretty useful things that might not make sense to put on stream verbatim, but could make sense to have on the side as a really useful thing, just as collectors have built-ins as well. So fold, for instance, it's an operation which is stateful, inherently ordered, and it's an n-to-1 operation. So if you know reduce, you sort of know this already. The main difference is that reduce is typically not ordered, and fold has an inherent order. In this case, it's left to right. So what does it do? So let's say that we have a stream of 1, 2, 3, 4, and we want to convert that into a string representation of the elements. So we give fold a supplier of the initial state, which is, in this case, the empty string. And then for each element, we get our current state, which is a string, the next element, which is an integer, and then we do string concatenation on that string with the integer. So what we end up with in this case, if we do find first on this, we get an optional of the string 1, 2, 3, 4. If we do it slightly differently, let's say that we want to sum these integers up instead, we would give a supplier of 0 as our initial state, and then we would take the current sum, the next element, and add the next element to the sum, ending up with the sum of the elements of the stream. So it's a very useful operation. We also have other things. Scan, for instance, also called prefix scanning in certain cases. And you can think of it as an incremental fold. So I'll show you. And this is a stateful, inherently ordered one-to-one operation. So for every element in, one element goes out. And let's say we have a stream of 1, 2, 3, 4. We do a scan. We give, just as in the fold case, we want to construct a string of the representation of the elements. And we want to create a list out of that. And that gives you one element for each partial accumulation along this path. So you could think of it as fold being scan, throwing away everything but the last piece. And you could do something similar here with the summation, right? So you get the partial sums along the stream. Can be really useful to get these partial results. Then, of course, see here, windowing functions. So let's say you want to group elements in a stream. Perhaps you want to group them 3 and 3. So we get 1 through 9. We get 3 groups of 1, 2, 3, 4, 5, 6, 7, 8, 9 as a gatherer. And of course, it's interesting because if you have situations where they do not cleanly partition into the groups, you will get, in the end, you will get one of the groups having the remainder. And that's good to know that you are not losing any data. And then, of course, beyond just windowing functions, fixed windowing is interesting, but sliding windows I find extremely useful. So let's say that you want to have you have a stream, you want to have a sliding window of 2, which means that you're pairing things up in a sliding fashion, so that first you get 1, 2, then you get 2, 3, you get 3, 4, and then it's really easy to do overlap checking. So let's imagine that this would be a stack trace, and you wanted to find where does this library call begin and where does that library call end. So it's a good way of finding where there are where you want to make a cut in things. And what's good about the sliding window thing is that it always gives you the full groups, presuming that the input is large enough. So in this case, we're sliding by 1 in every case. So 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6. I find it useful anyway. And my favorite, let's imagine that you wanted to have map concurrent. You want it to be able to take your stream and do something concurrently up to a specific limit, sort of like a rate limit thing. And you want it to make sure that it still keeps order and it doesn't require much in terms of doing things around. So you can package this as a gatherer. So imagine that you have a stream of the numbers 1, 2, 10, 20, 30, and 40. Trust me, it will make sense in a couple of seconds. So let's say that we want to run each element 2 at most at a time. And for each element, we want to sleep. We want to sleep for 1 second per n. So the first will sleep 1 second, the second will sleep 2 seconds, the third will sleep 10 seconds, and so on and so forth. And just to prove that it actually works, I am adding a system out print line here to inform that the task was interrupted. And then I restored the interrupt, important stuff. And then I returned the n. Very important work being done here. So if we only want 2 of these things in the end, how much work would you expect to be done? We only want 2. We have 6 elements. We want 2. In the end, we get 1 and 2, and we get 10 and 20 interrupted. Because as we were emitting when 1 was done, we started 10. And when 2 was done, we started 20. But then we figured we didn't need anything more, so now we can cancel that work. And this specific example is using virtual threads under the hood, so you could, if you're running this within a virtual thread itself, the sleep is what it is with virtual threads. So, 3 minutes left. The plot thickens here. So what's interesting here is we have these gatherers, and they can represent an operation, but it would be extremely nice if we could actually connect them together so that a gatherer could represent multiple simpler operations. So let's imagine that we have something that parses ints, so strings to optional of integers, and then we have something that drops empty ints. So we want to take the optionals that are empty, discard those, and just get the integer out. So we could get from the stream 1, foo, and 2, we first parse the ints, we drop the empty ints, do the to list, we should get 1 and 2. But if we wanted to reuse this, we could compose these 2 operations. So instead of doing gather the first and then gather the second, we can do the first and then the second, just as you can do with a function and compose a function. And now you can pass those around and reuse them, stash them into static finals. So if you think about it, if gather.gather.gather is the same thing as gather and then from a philosophical standpoint, if we can represent almost any intermediate operation that we could imagine, and we can compose them together, that means a stream pipeline is sort of a source, an optional gatherer, and a collector. So it's an interesting way of thinking about it. So to summarize this, what have we gathered here? I'm terrible at puns. I apologize profusely. Gatherers support everything that we wanted. Everything that we wanted. And to summarize, gather and gatherer is an extensible API for intermediate stream operations, representing stateless or stateful operations, supports any-to-any, consumes as much input as needed, and can be evaluated sequential or in parallel, and can be reused and remixed. Thank you. Yes.
The downstream, that's essentially the next step of the stream
Yes.
pipeline, right?
Yes.
So, and how do you get that when you, like when you're setting up a stream?
Yep.
Like, do you basically set it up going backwards, so you always have the next stage when you're composing into the previous stage, right?
Great question. So the question is, how do you create, or when do you create the downstream? So what's interesting about streams is that it is a builder. So you get to build this up, and it doesn't do anything until you add the terminal operation. So when you add the terminal operation, you know what the pipeline is. And then you can reverse order, create the downstream handle, and pass that in. So it's an interesting artifact, but the model needs to know what the next step is in order for you to do anything. But yeah. Thank you.